Here's a structure. You can count the number of links or number of beams. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Count the number of joints. The question is, given this truss and the information shown here, find the member forces. Everybody with me? Where do we start? Where do we start? Okay, you want to start at A. Why? Because there is an applied load that we know, and there are two unknowns, and we solve for these two. Then what do we do? You want to go here? Okay, you go here. How many unknowns are there? How many members are coming in here? 1, 2, 3. And then there is a support reaction. So there are 4 forces, of which one of them is already calculated. So there will be 3 unknowns. Can we solve? Nope. So we are stuck here. You want to go there? Doesn't help. You want to go there? Doesn't seem to help out either. What do you want to do? I mean, you can calculate this. That's a good response. But it doesn't take you anywhere. So what do we do next? We are stuck. We need to find out the member forces everywhere. Well, go to C, you find this again, you cannot go here or here. Same situation. In fact, if you look at this particular problem is symmetrical. 4 kips here, 2.4 kips here, right in the middle, and this is symmetry. So, same scenario. You solve for C, you will find this member force, you will find this member force, but then you are stuck again. In fact, if you solve for this, you don't have to solve for this because it's going to be exactly the same. So, what do we do?
Make it a box and try to solve that.
I want you to reframe it. Say that again properly so everybody can understand. What he is saying is, consider this instead of a box. I would like to use a better technical term. Use the complete structure, but disconnected from the joint. Disconnected from the supports. That means we'll have 3 unknowns, and it is a 2D rigid body equilibrium problem. 3 unknowns. You know there are 3 equations, so you can solve for them. Once you know these members, now when you come here after solving this, how many unknowns will be there? Already the support reaction is known. This is known, there will be 2 unknowns. Do you understand that? So the strategy for this problem is, you are unable to find a joint that will help you to solve the whole problem. If that is the case, you could have done that like the previous problem. So in this case, what we want to do is to consider the entire structure, but disconnected from the support and calculate for support reactions. So this is the first step. So let me draw the free body diagram of the entire system, which is exactly what you see here. And I should not ignore any of the member forces, so I am drawing them here, which is 4 kips. And this is 1 kip. And again, A, B, C. And here is again, I have an applied load, right? Here I have my D, D sub y, and this will be E, F sub y. And let's say this is my coordinate system, and I have my length, and that's a complete free body diagram. On point F. Yeah.
F sub x.
Yeah, sure. Agreed. Thank you. So, all of you find this free body diagram understandable? No confusion. Okay. Do not miss these things. Do not just draw a box and say that's the same as that. You got to redraw the whole thing and don't be lazy about it. The only thing you have disconnected is the support reactions. So what we are going to do is now the first part of analysis. Calculate the support reactions. Sum of the forces along x direction, you can make it 0. Interestingly here, sum of the force along x direction is also f sub x, and that happens to be 0 because there is no horizontal component. Does it make sense? You can say sum of the forces along y direction equal to 0. So you will have dy plus fy, right, equal to, these are all negative forces, so 1 plus 4, 5 plus 1, 6 plus 2.4, 8.4. So this is my first equation already resolves. This is my second equation, but I have two unknowns. So what do I do now? Moment about what? You want to take moment about f? Okay. I was hoping to take about this, but this guy's creating trouble, so let's follow what he said. It really doesn't matter, right, boys and girls? So let's take moment about point f as he wanted, which means there won't be any moment due to f sub y, and there is no moment actually due to f sub x because which itself is 0. And there won't be any moment due to one kip because the line of action passes through the point of interest, leaving you have 1, 2, 3, 4 components of moments with one unknown, so we should be able to solve. So let me start here. So I start here, I'm going to go here, 4 kip, that's going to give a counterclockwise, so plus 4 times this distance, which I believe is 12 feet. Then I go to the next one, plus 2.4 kips, right, times again the same distance. Then I go to the next one, which is this 1 kip, which is again counterclockwise, so plus 1 times this distance, which is 24. And then the last one is dy, which is going to give a clockwise, so it's negative dy times what's the distance? 24 equal to 0. And this equation has got only one unknown, so d sub y equal to, can you say that louder? I can't hear it. 4.2 kips. And that's direction assumed is correct. So if dy is 4.2 kips, then fy should be also 4.2. This must tell you this system is symmetric. In fact, when you look at the system itself, you should say this must be equal to that, and that's the reason I knew this was 0. So when you look at problems like this, don't start doing everything. When you see symmetry, take advantage of symmetry. That means the question is calculate all the member forces. That means all I have to do is to calculate this member, this member, this member, and this member, and this member. The rest of them will be exactly the same as the other respective member. You could start this side, it doesn't matter. So you don't have to do everything. You just have to calculate 1, 2, 3, 4, 5 members, and the other 4 members will be equal to that. This is a common member.
But we should only do that after we've separated the support.
Well, you still have to calculate this. Okay. So in other words, you could do that before, but the point is you don't know these two support reaction, and that's the purpose of this. Yeah. Okay? Make sense? All right. So we calculated the support reactions. So what do we do now? Remember, what are we trying to do? We are trying to calculate the member forces. And we haven't even started. We are doing something else. So what do we do now? Where do you want to go? Point A, joint A. Okay? I would like to use the word joint. Okay? So we'll draw the free body diagram of joint A. Okay? That's my joint A. Can someone help me with this free body diagram first? Force in member AB going which way? To the right. Force in member AD. And the reason we are doing this is because we assume member AD and member AB are in tension. If it is not, we'll get a negative answer. And we are not going to think, oh, it's in tension. Remember, if I look at this member AD, I can tell you by obviously it is in compression. But I'm just not going to do this. I'm just going to consistently assume every member is in tension and then move forward that way. That way, there won't be any confusion. And there is no other member, but there is also an applied load, which is 1 kip. And I must state that. And here is my coordinate system. Will I be able to solve this now? Somehow the forces along x direction equal to 0. And there is only one force along x direction, so F sub AB will be equal to 0. So that member is a zero force member. Got it? And we'll talk a little bit more about what a zero force member means a little bit later. But our calculation tells this member doesn't carry any load, it is a zero force member. At least mathematically it should be obvious to you. I'll talk about the physical meaning behind it in a few minutes. Okay? What else we can do now? Somehow the forces along y direction should be equal to 0. So minus FAD minus 1 is equal to 0. So FAD is equal to minus 1. Are you with me? All right. What does it tell you? That means member AD is in compression. Got it. Make a mental note. We'll revisit that later. But right now, leave that negative 1 alone so that we carry that all the way through. Okay? All right. What do we do next? So we calculated two member forces. What's the next one? Member? Which joint? Joint D, because obviously that's not helping, right? So we go to joint D. So let's say joint D, free body diagram of joint D. All right, so I draw the joint D. What do I do now? Member AD will be going FAD, and then there is, I'm going to write this on this side, FAD. Then there is a member going this way, which is force BD, DB, any way you want. Okay? And then member F, DE. Am I done? No. What is left? D sub y, right? Which is equal to what? 4.2 kips. Since it is a support reaction, so I'm going to put that value right there. We know this member force, we know this support reaction, that leaves us two members, and therefore I should be able to solve. But I cannot solve it because I'm missing this angle. So I go back to the original diagram and say, what do I do now? Because this is an incomplete free body diagram. I got my axis, I got my forces all done, except for the angle. So what is this angle? There we go. You got your triangle, 6.4 over 12, tan of that. 28 degrees. 28 degrees. So I go back here and this is going to be 28 degrees. So all I am going to do is to somehow the forces along x direction should be equal to 0. So that would be FDE plus FBD cosine 28 degree. Any other x component? Nope. Equal to 0. Realize I do not know FBD and I do not know FDE, so there is an equation with two unknowns. Can't do anything. So move on to the next step. Somehow the forces along y direction should be equal to 0. Correct? And that would give me 4.2 kip plus FAD equal to, no, not yet, plus FBD sine 28 degree equal to 0. And I already know this value. All right, so I'm going to write the equation in terms of FBD, which will be equal to negative FAD minus 4.2, am I right? Over sine 28 degree equal to minus FAD, which is going to be negative, and this will be negative 1, right? Negative 1 minus 4.2 sine 28 degree. Can you tell me what you get? It will be negative 3.2 divided by sine 28. Hello, people? Negative 6.8. Okay? So that tells me member BD is in compression. All right, so I have found out two members, this member, as well as this member. So we need to now, so if I know this, all I have to do is to substitute this here. This is my second equation. And from this equation, I should be able to calculate FDE. Has anyone done that? 6. Plus 6, right? Plus 6 kips. Okay? So I have solved for all of those except for the last member, which is BE. How do I solve for that? I need to solve for this member. You could do B. I would like to make an easier thing. So joint E will be easier, right? So let's draw a free body diagram of joint E. And joint E will have 3 members coming in, F sub BE, and this will be your F sub EF. This is your F sub DE, and there is an applied load 2.4 kips. And that's my free body diagram. Realize we already calculated this, which is equal to 6 kips. And they are lined up, and this is equal to that. And therefore, FEF equal to FDE equal to 6 kips. But I'm interested in this member, which is FBE, which will be equal to 2.4 kips. So the final answer is member AB is a 0 force member. Member AD equal to what? 1 kip. 1 kip is a tension or compression? Compression. Then member BD equal to what? Did we do that? Negative 6.8 kips. So I'm going to write 6.8 kips. Tension or compression? Compression. Finally, member F DE is in tension, and it is going to be 6 kips. And the last one is member BE equal to 2.4 kips in tension. This is your answer.